As we progress in talking about indices and logarithms, we now look at index algebra in this video. Index algebra. Okay. So for index algebra, our learning outcome include the following. By the end of this lesson, we want to be able to manipulate expressions with indices strategically, including factorizing with indices, um, simplifying with variables and parameters, comparing sizes of exponential expressions, which I think is extremely important, and solving index inequalities. Shall we? So first of all, we look at factorizing with indices. I think yeah, I mean, it still plays into some of the things we had learned before now. Factorizing means rewriting an expression as a product. And the key law we are going to use here, so you can see this product law is pretty important. Product law of indices. So a raised power m times a raised power n is equal to a raised power m plus n. It's really, really important. Okay? Because technically, right, if you have as we have that a raised power m plus n like that, we can write it as a raised power m into a raised power n. It's some kind of factorization, if you like. So in the same way, if you have a raised power m plus n still, we can write it as a raised power n into a raised power m. It is still some kind of factorization. And that's the idea we are going to apply as we talk about factorizing with indices. So imagine a common factor method. We have this example one now. If you need to factorize ax plus ay, you know, what matters is x and y, the values of x and y, because of course a and a are already the same, so we don't have much to do with that. But the power is really important. If x is greater than y, that means y is smaller than x, right? So what we need to do is you factor out the smallest power, which is a raised power y, taking it that because they have the same base. If a has the smaller power, it means a raised power y is smaller than a raised power x. So factor out the smallest power ay, which is a raised power x plus, I think this English, this word is better as smaller power, right? Factorize out the smaller power. Okay, so factor out the smaller power, a raised power y. So you have a raised power x plus a raised power y. That will be equal to a raised power y into a raised power x minus y plus a raised plus 1. The explanation is you have a raised power x divided by a raised power y equals a raised power x minus y. Of course, what we are simply saying is that you have a raised power x plus a raised power y and and x and y, let me put it this way. X is greater than y, meaning that y is less than x. Okay. The fact that y is smaller than x automatically, uh, okay. I mean, that's the question you have. You want to factorize, right? So since, since y is less than x, it means that a raised power x is greater than a raised power y. Or, I mean, that's the same thing as saying a raised power y is less than a raised power x. Okay, so we're going to see that comparison thing very soon. So what do we do with that? We know that a raised power x plus a raised power y, okay, is equal to the smaller power now is a raised power y. So you have a raised power y. The smaller power is y. So that means a raised power y into a raised power x over a raised power y plus a raised power y all over a raised power y. Okay, that means we have a raised power y into, I mean, from the law, from the quotient law of indices, we can say this is a raised power x minus y plus a raised power y over a raised power y. Well, this is simply one, or if you want to go the trouble way, you can say a raised power y minus y. Okay, we already know that's one, right? So that means a raised power y into a raised power x minus y plus a raised power 0. Okay, so that means a raised power y into a raised power x minus y plus 1. And that is what a raised power x plus a raised power y would mean for that's when x is greater than y. I mean, the other way around, we also have it, we follow the same rule. What if we now have to factorize, you have ax minus ay, assuming that x is greater than y. That means y is less than x now. Okay, so here we have ax. So it's still the same thing, except that this is now negative. So ax minus ay is simply ay into a into x minus y minus 1. And that's the deal here. So imagine this now. Factorize 3a squared plus 6a squared. Of course. So for the numbers, you pick the smaller number, especially if the small a one that is that is one of which the other is a multiple. I think that's a better way to say it. And for the indices now, look at the smaller index. So the common factor here for 3 and 6, 3 is common. For a raised power 5 and a raised power 2, a raised power 2 is common because a raised power 2 has the smaller power. So you have 3 a raised power 5 plus 6 a raised power 2 equals 3 a raised power 2 into 3 a raised power 5 over 3 a raised power 2. That's a raised power 3 plus 6 a raised power 2 over 3 a raised power 2, which is simply 2. So what I've said there is you have 3 a raised power 5 plus 6 a raised power 2, right? 3a raised power 5 plus 6a raised power 2. So between 3 and 6, the common factor is 3. For a raised power 5 and a raised power 2, the common factor is a raised power 2. So you now have 3a raised power 5 all over 3a raised power 2 plus 6a raised power 2 all over 3a raised power 2. So this and this will go. So you have 3a raised power 2 into 3 cancels 3, and then you have a raised power 5 minus 2 plus 6 divided by 3, that's 2. Okay, that means you have 3a raised power 2 into a raised power 3 plus 2. And that's what we have on that page right there. Okay, so we can then talk about difference of powers. So that was common factor method. What about difference of powers now? Yeah, I have on many occasions I've talked about difference of powers, difference of squares rules, that a squared minus b squared is a minus b plus a plus b, right? I mean, a squared minus b squared is equal to a minus b multiplied by a plus b, to be clear with that. So to factorize this now, we know a raised power 2x minus 9 can be, so 9 can be written as 3 squared, while a, a raised power 2x minus 9 can be written as a raised power x times 2, from the law of power of power, a raised power x raised power 2 is the same thing as a raised power 2x minus 9, which is 3 squared. Then you can use difference of two squares now, where you have ax minus 3 into ax plus 3. So that works here too. Then for example 5, you want to factorize a raised power 4 minus 16. That's a raised power 4 minus 16, which is a raised power 4 can be a squared squared minus 4 squared. All right, so that we can have a squared minus 4 into a squared plus 4. Now, that's not the end of it, because if this 4 is also a square, a squared is a square. So you have a squared minus 2 squared into a squared plus 4 squared. So you end up having this. I feel I should just do it on the worksheet. A raised power 4 minus 16. A raised power 4 minus 16. Using this concept, a raised power 4, you have a raised power 4 minus 16. So first of all, we know this can be written as a squared squared minus 4 squared, right? So that means we have a squared minus 4 into a squared plus 4. First of all, going forward, we know we can also write this as, this is the same thing as a squared minus 2 squared into a squared plus 4, which that one we cannot do anything with it. Well, we can do something with it, but it's not necessary. So we then have a minus 2 into a plus 2 for that first one into a squared plus 4. So ultimately, we have a minus 2 into a plus 2 into a squared plus 4, like that. Okay, so with that in place, we can go ahead and talk about simplifying with variables and parameters. So what if we have to simplify with variables and parameters? So we have index laws here. The index laws are simply the products of indices, the quotient of indices, and the power of powers, right? So or power of power, if you like. So you have a raised power m times a raised power n, that's a raised power m plus, and a raised power m divided by a raised power n, that's a raised power m minus, and a raised power m raised power n is a raised power m times n. And then example 6 tells us that we can have we can simplify. So we have a raised power x plus 3 all over a raised power x minus 2. So using the law of the quotient of powers now, we can just subtract the powers. So we have a raised power x plus 3 minus x minus 2. That means you have a raised power x plus 3 minus x plus 2. So x cancels x, 3 plus 2 is 5. So we have a raised power 5 like that. Then for example 7, we simplify. We have a raised power x raised power 3 times a raised power 2x. That means we can say this is a raised power x raised power 3, that's a raised power 3x Then we have a raised power 3x times a raised power 2x. We can add 3x plus 2x, that's 5x. That means we have, for this, we have a raised power 5x. For example 8, we have a raised power 2x, b raised power 3, or all over a raised power x b. So for the a's, we have a raised power 2x minus x. For the b's, we have b raised power 3 minus 1. So 2x minus x is x. So a raised power x, b raised power 3 minus 1, that's b squared, like that. So example 9, similar thing can happen. We can simplify. We say x raised power m plus 2, y raised power m, all over x raised power m, y raised power m minus 1. What do? We say x raised power m plus 2 minus m, okay? Because we are dividing. So m plus 2 minus m. So m cancels m. So we have x raised power 2. Y raised power m minus m y raised power m minus m minus 1, because we are dividing this. So we have y raised power m minus m plus 1, because minus and minus will be plus. My m cancels m, so we have 1. So this whole thing is given x squared multiplied by y, x squared y. Now we've come to a very important part, which requires some more attention than all the ones we've been doing. So how do you compare sizes when you're working with indices? So you want to know which quantity is larger for two numbers in index form. So the strategy is, if the bases are the same, you can compare the powers, right? If bases are the same, so assume that you have bases are the same. Say you have 3 raised power something, and you have 3 raised power something. So you compare the powers to themselves to see which one is bigger. For instance, as far as it is settled that the base of the two is 3. So it doesn't matter that this one is written larger, it doesn't matter anything. So imagine that you now have this to be minus 2, and this is minus 1. Okay? So, of course, we know that minus 2 is less than minus 1. So as a result of that, 3 raised power minus 2 is less than 3 raised power minus 1. That's what that means. So, or if you like, we have 10 here, you have 10 here. So, and then the power of this one is 7, and the power of this one is 3. Okay? So since 7 is greater than 3, so it means that 10 raised power 7 is okay. So here, what did you decide? We know that minus 2 is less than minus 1. Okay. So since 7 is greater than 3, that means 10 raised power 7 is greater than 10 raised power minus 3. Like that. So that's our first rule that we saw there. On the other hand, right, if powers are the same, you compare the bases. Okay. If the powers are the same, you then go ahead and compare the bases. So imagine now you have something power 5, and you have something power 5. Powers are the same, confirmed. But then if these numbers now you have to compare. So let's imagine that we have 5 raised power 5, and then we have uh, 7 raised power 5. Okay? Because 5 is less than 7. That means 5 raised power 5 is less than 7 raised power 5. Okay? So that's so if powers are the same, right? Or imagine if you have something power minus 2 and something power minus 2. Okay. I think this is another dimension to it. If the powers are the same, okay, let me just say 2 here, okay, and this is 3 here. So this is 1 over 4, and this is 1 over 9. So definitely 1 over 4 is bigger. So I think even the power, we have to be sure it's not positive or negative power. So I think it has to be, I think that power rule only applies to the positive case. So if powers are the same, compare the base. We write the expression using a common base. So these are strategies. So if powers are the same, compare the bases. Well, so the deal here is this: if the powers are the same here, minus 2 minus 2, I think the rule has to be made for negative values and positive values, because 2 raised power 2 and 3 raised power 2 now. 2 raised power 2 is obviously less. But once the powers change, once you invert it like this, the power will change, because 1 over 4 is bigger than 1 over 9. So I think you have to pay attention. If the powers are the same and they are negative, the smaller base will the smaller base with that power will be greater than the bigger base with the same power. But if the powers are positive, the smaller base with that power will be less than the bigger base with the power. So I think there's something to be said about whether the power is positive or negative. Okay. So let's look at example 10 now. Compare 2 raised power 5 and 2 raised power 7. Of course, the bases are the same. So, and 7 is greater than 5. So it automatically means that 2 raised power 7 is larger than 2 raised power 5. For example, 11, you have okay, you have 4 raised power 3 and 2 raised power 5. At first sight, this may not be easy to decide. Of course, these are simple, small numbers. So we know to say that 4 raised power 3 is 64 and 2 raised power 5 is 32. So this is bigger. But what if it's some number that you can't know at first sight? So you have to write them at the same to the same base. First of all, we know 4 is 2 raised power 2. That means 4 raised power 3 is 2 raised power 2 raised power 3, which is 2 raised power 6. And that's clearly bigger than 2 raised power 5. So 2 raised power 6 and 2 raised power 5, is what we are comparing. That means 2 raised power 6 is larger. So it's either you get the actual expressions and compare, or if you want to use base, make sure the bases are the same, like that. Of course, there's a way you can also write 2 raised power 5 as 4 raised power something, because this would have been 4 for I mean that's harder, right? So I think it's just easier to go the other way. Okay, so example 7, you want to compare 3 raised power 10 and 5 raised power 7. Well, I mean, you can make them come to the same base, but that's a difficult procedure. So the easiest thing is just get the actual values. 3 raised power 10 is 59049. Then 5 raised power 7 is 78125. And it's clear that 5 raised power 7 is bigger in that case. All right. So we can say 5 raised power 7 is bigger than 3 raised power 10 in that regard. So what if you want to talk about variables now? You want to compare variables. Okay, I think that this is hard. This was the issue I ran into the other on the worksheet. So imagine you want to compare a raised power 6 and a raised power 9. If a is greater than 1, that is, if this a now is a big number. So a raised power, because this one now has if a is bigger than 1, that is a number bigger than 1, right? So the powers will matter. Like, so a raised power 9 will automatically be bigger than a raised power 6. So, but if a lies between 0 and 1, of course, that'll now be like a fraction. So let's say a is like half. So half raised power 6 is clearly bigger than half raised power 9. So that's like 1 over 2 raised power 6. That's clearly bigger than 1 over 2 raised power 9, for sure. So that's also something we need to pay attention to. So always consider the value of the base. So in fact, both base and power. So if you are comparing power uh, or base, make sure be sure of the value, whether they are greater than 1 or less than 1, or some, or between 0 and 1, all those kind of thing. Okay, or maybe they are even negative. So let's go ahead and talk about index inequalities. So if we have same base to be greater than 1, say if you have a to be greater than 1 and you have a raised power m greater than a raised power n, this simply implies that m is greater than n, basically. So you want to see, so now we are comparing power. We are done. So if a is greater than 1, we already know m is greater than n. But if a lies between 0 and 1, right, it means that it is going to be reversed. Yeah. So example 14 now. Imagine example 14. You want to solve 2 raised power x plus 1 greater than 2 raised power 5. So they have the same basis, right? So since they have the same basis, and we have said that this is greater than this. Basically, since they have the same basis, we have to then know that since the base is bigger than 1, it means that x plus 1 will be bigger than 5. So x plus 1 is greater than 5. That means subtract 1 from both sides. So it means the x here has got to be greater than 4. Okay? So if x is less than 4, this inequality cannot hold anymore. In fact, if x is 4, 2 raised power 4 is not bigger than 2 raised power 5. So x has got to be bigger than 4, right? So if it's 5, for instance, then you can have 2 raised power 6 bigger than 2 raised power 5. So if you have something between 0 and 1, like if the base is between 0 and 1, then the inequality will have to reverse. I think I talked about this in an example, like you have 1 over 2 raised power x greater than 1 over 2 raised power 3. Yeah. So if this is greater, that simply tells us that x will have to be less than 3 in this regard. because we have the same base now, but they are fraction. So in this case, the reverse is the case. So if this is bigger than this, it means that the power here has to be smaller, because for a fraction, the bigger the power, the smaller the overall number is going to be. For instance, 1 over 2 raised to power 4 is smaller than 1 over 2 raised to power 3. So if you are dealing with a fraction, the smaller the power, the better. So since you have to be less than 1, you have to reverse the inequality that x has got to be less than 3. Okay, so s has to be less than 3, because 1 over 2 raised to power 2 is 1 over 4, and that is less than and that is greater than 1 over 8, So you can also rewrite to same base. So to rewrite to same base now, okay, I think this is a long one. So can I still fit everything in? Yeah. I think, yeah, as much as possible. So look at this now. You have 4 raised power x greater than 8. So how do you decide? So 4 raised power x is 2 raised power 2. 8 is 2 raised power 3. So 4 raised power x is 2 raised power 2 raised power x. And that's greater than 2 raised power 3, right? So we already know 2 is bigger than 1. So the only sensible thing here is for 2x to be greater than 3. That means x has got to be greater than 3 over 2. For this to hold, x has to be greater than 3 over 2. All right. Because if x is 3 over 2, for instance, it means we have 8. 8 is not greater than 8. So x has got to be 8, at least a little bit more than 3 over 2 for this expression to hold. So I think that requires some serious attention when you have. So that can be a trick question in many aptitude exams, or maybe SAT or GRE or something like that. So for example, 17, now you have 3 raised power 2x less than or equal to 27. So right to the same base, so it's easy to compare. So 27 is 3 raised power 3. So that means you have 3 raised power 2x less than or equal to 3 raised power 3. So these 3 and 3 are bigger than 1. So you can just literally take it to be that 2x is less than 3 in that, less than or equal to 3. So that means x is less than or equal to 3 over 2 also in that case. So once you conclude that the base is bigger than 1, then you can just take whatever sign you have here, you can apply to the powers also. So what's the strategy here? The summary for our strategy here is: number 1, factorizing. You can take the smallest power as a common factor, simplify and apply index laws carefully, and subtract powers when dividing. Then comparing sizes, rewrite in a common base like we've been doing. For inequalities, now the base greater than 1, direction stays the same. For inequalities, that is base is between 0. For inequalities with base between 0 and 1, you have to reverse the inequality sign, right? So like in this case now, we discover that the basis 3 is bigger than 1. So for the powers now, you can maintain the same less than or equal to here. But I think there was in this case now, you see that half is less than 1. So instead of keeping x greater than 3, no, x has to be less than. So you reverse that inequality. That's what that means there. So let's try our hands on some practice problems. As usual, let's take them in fives and see what we can do. So practice problem, factorize this. Of course, this will just be a raised to power 3 into uh, a raised to power 5 minus 1, Then for this, you want to factorize a raised to power x plus 4 plus a raised to power x. So you just take a raised to power x into a raised to power 4 plus 1. Then factorize completely 4 a raised to 6 minus 12 a2. So 4 is common for 4 and 12. A2 is common for a6 and a2. So you have 4a2 into a4 minus 3. Then factorize b2x minus 25. That will be bx raised to power 2 minus 24 minus 5 raised to power 2. That will be bx minus 5 into bx plus 5. Then factorize fully a raised to power 4 minus 81. Okay, I think this is going to be a sweet ride. A raised to power 4 minus 81. It's not just one step. So you have a raised to power 4 minus 81. So that means you have a raised to power 4 minus 3 raised to power 4. So, and that means you have, that's a raised to power 2 squared minus 3 raised to power 2 squared, like this. So that means you have a squared minus 3 squared into a squared plus 3 squared. Okay, so we can then say again, this is a minus 3 into a plus 3 into a squared plus 3 squared. Okay, that was the type we did previously with one of those questions. Okay, so here you want to simplify. Okay, let's go 6 to 10 now. If you can take them at once. Okay, which one should I take? Okay, well, we can even still take this one straight. That's a raised by x plus 7 over a raised by x minus 2. That's a raised by x plus 7 minus x minus 2. That's x plus 7 minus x plus 2. So x cancels out. So we have a raised power 9. That's what this is going to give us, a raised power 9. Then to simplify this, we have a raised power 6x straight up. Then for this, we have a raised power 3x over ax. That's a 2x b2, right? b4 minus 2, b2. Then for this, now we have a raised power 2x times a raised power 5x. That's a raised power 7x. For this, okay, let's do some mental stuff. So we have m plus 5 minus m plus 1. So that will be x raised to power 4 because m will cancel, but 5 minus 1 is 4. So x raised to power 4. Then for the m also cancels out. We have minus 2 plus 3. So x 4, y 1. X 4, y 1. Then 11 to 15. Let's also see if we can do some mental work with that. Which is larger, okay? Of course, 2 raised to power 9 or 4 raised to power 4. 4 is 2 raised to power 2. That'll be 2 raised to power 8. So 2 over 9 is larger than 2 raised to power 8. 4 raised to power 4 is simply 2 raised to power 8. Then which is larger again? 3 raised to power 8 or 9 raised to power 3. So this is 3 raised to power 3. So that'll be 3 raised to power 9. So 3 raised to power 9 is larger than 3 raised to power 8. Which is larger? If a is greater than 1, okay? Because a is greater than 1, of course, a12 is larger, a raised to power 12 is larger than a raised to power 9. Which is larger if a lies between this. So of course, for if a is between this, it means the smaller power is larger than that. So for a between 0 and 1, a raised to power 5 is bigger than a raised to power 8. We want to solve this. Of course, to solve it, because the bases are the same and they are greater than 1, we can just say we maintain the direction. X plus 1 is greater than 4. That means x is greater than 3 in that case. And that makes sense because if x is 3, 5 raised per 4 is not greater than 5 raised per 4. But if x is greater than 3, that means we have at least 4 plus 1. 5 raised per 5 is greater than 5 raised per 4. Then 16 to 20, if you can fit all of that in at once. So you want to solve this. Okay, this is not even an inequality. So to solve this, of course, you can compare the powers. 2x equals 7. That means x is 3 over 5 or 7 over 2. Then to solve this, because 2 is greater than 1, so you can just maintain the direction. X minus 3 is less than or equal to 5. That means x is less than or equal to 5 plus 3. That's x is less than or equal to 8 in that regard. So to solve this now, of course, 1 over 4 is 1 and 1 over 4. 1 over 4 lies between 0 and 1. So you have to reverse the direction. That means x has to be less than 6 for this to hold true. Okay. Then to solve 9 raised by x greater than 27. So this is 3 raised by 9 is 3 raised by 2. So 3 raised by 2x. Yeah. Oh, did I make a mistake somewhere? I saw 1 9 somewhere. Okay, this is yeah, this I think I made a mistake here. This is 9. 9 is 3 raised power 2. So this is 3 raised power 6 and 3 raised power 8. So 3 raised power 8 is larger. Sorry, my bad. So I think I said 3 raised power 3 the other time. So it is 3 raised power 2. That would mean 3 raised power 6 overall, and this is 3 raised by 8, and this will be bigger than that. Okay, this just reminded me of that now. Okay, you have 9 raised by x greater than 27. That means you have 3 raised by 2x greater than 3 raised by 3. So because 3, the base is bigger than 1, so it means 2x is greater than 3. That means that x is greater than 3 over 2. And to solve this, the base of this, we can make it, well, you can keep it at 4. Yeah, if we do 4, we just say 4 is raised by 2x, 4 raised by 2. So because 4 is bigger than 1, so we can say 2x is less than or equal to 2. And that means x is less than or equal to 1. We can also do 2 raised by 4 is 2 raised by 2. So we have 2 raised by 4x, 2 raised by 4. So same thing, 4x is less than or equal to 4. So yeah, with that, we come to the very end of this interesting video on index algebra. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed, already, thank you very much. If you haven't subscribed, what are you waiting for? Subscribe, hit the notification bell so you can always get alerted each time a new video is released. Beyond that, you can also become a member of this channel by clicking on join. That gives you some special privileges like seeing some videos first or being the only ones to see certain videos. Ultimately, don't forget to comment, like, and share. Till next time, keep doing maths right. Bye.